Ever wonder how AI models like GPT or Llama really process language? It's not magic, it's math, and it's more fascinating than you might think. Today, we're diving into a breakthrough technique that's helping scientists decode the hidden logic of these models. Let's break it down. So here's the thing. AI models are made up of layers of artificial neurons, like tiny brain cells. But here's the catch. Each neuron doesn't just think about one thing. They're juggling multiple ideas at once, like a musician playing multiple instruments in a band. Hard to tell what each one is contributing, right? For years, researchers tried to understand these models by looking at individual neurons. But that's like trying to figure out a symphony by listening to one instrument. It didn't work well. Then scientists had a breakthrough. Instead of focusing on single neurons, they started looking at directions in activation space. Think of it as studying how groups of neurons work together to represent concepts. But here's the problem. Existing tools like sparse autoencoders, SAEs, could find patterns, but they couldn't always explain why those patterns mattered. It was like finding a treasure map, but not knowing where the treasure was. Enter SNMF, Sparse Non-Negative Matrix Factorization. Imagine you've got a messy pile of puzzle pieces. SNMF sorts them into clean, meaningful groups. It takes the complex signals in a model's MLP layers, the parts that process information, and breaks them down into sparse, interpretable features. These features are like building blocks. Each one is a unique combination of neurons, and they're tied directly to the inputs that trigger them. Here's how it works. When you feed text into a model, the MLP layers light up in specific patterns. SNMF splits those patterns into two parts. One part is a set of features. Think of them as concept detectors. The other is a map, showing how much each feature contributes to different parts of the text. This makes the features causally interpretable. You can actually see how changing a feature affects the model's output. For instance, if a feature is linked to programming, activating it makes the model write code snippets, not just random words. And these features aren't isolated, they're part of a hierarchy. A JavaScript feature might feed into a broader programming concept, showing how the model builds meaning step by step. In experiments, SNMF outperformed SAEs and even strong supervised methods at tasks like causal steering. Researchers tested whether features could guide the model to generate text about specific topics. The results: SNMF features were more accurate and meaningful. They weren't just math tricks, they were capturing real patterns in the data. But SNMF isn't just about understanding models, it's about reshaping how we interact with them. By isolating these features, we can audit models for bias, debug errors, or even fine-tune their behavior. Imagine a world where AI's decisions are transparent, where we can ask, why did this model generate that response? And get a concrete answer. This ties into a bigger idea. AI models don't just memorize words, they build geometric maps of meaning. Think of it like a city where each street represents a concept. A dog might be near pet and fur, but far from car or planet. This geometry of concepts helps models recognize patterns, like knowing a cat is more like a dog than a computer. How do these maps form? It starts with sparse representations, like how your brain focuses on a friend's face in a crowd, ignoring background noise. Studies show AI models activate just a tiny fraction of their neurons, picking out the most important features. It's like a spotlight shining on what matters, making their learning efficient and adaptable. Researchers are testing these ideas with tools like non-negative matrix factorization, NMF, and autoencoders. NMF is like sorting a messy room. It breaks down complex data into simpler, meaningful parts. Autoencoders, meanwhile, act as AI's self-help tools. They compress information into a summary and then try to rebuild it, learning what's essential along the way. Surprisingly, even when trained on the same data, different autoencoders can focus on entirely different features, like two people describing the same painting in unique ways. This isn't just academic, it's shaping the future of AI. By understanding these internal maps, scientists can make models more transparent, fair, and reliable. For example, if we know how a model distinguishes bias from accuracy, we can fine-tune it to avoid harmful outputs. It's like giving AI a compass to navigate ethical dilemmas. And here's the kicker. What if we could ask the AI itself to explain its thinking? A 2021 study showed models can generate human-readable descriptions of their own decisions, like saying, "This neuron fires when it sees a cat's ear." It's like giving the model a voice to explain itself, though it's not always perfect. Tools like Neuronpedia are turning this into a shared encyclopedia for neural networks, making the black box a little more transparent. So next time you interact with an AI, remember, it's not just spitting out words. It's building a world of meaning, one neuron at a time. Thanks for watching, stay curious, and keep exploring the math behind the magic.